Hello guys, let us continue again on our lesson. This is a continuation from the energy, kinetic energy, gravitational potential energy chapter. So this will be about power. So what is power? Power is basically the rate of energy being used. That means how much energy is being used for a certain period of time. So in other words, when an energy is being used, it can be any form of energy. It is being used for let's say 10 seconds. So that act is also known as the power. So there is a power being used for that certain period of time. All right. So bear in mind also that whenever the word rate is being used in physics or sciences, we are always talking about the change of a physical quantity over time. So power is measured in joule per second or watts, capital W. Okay, the formula for power is as shown, energy per time. So that energy can be in any form. It can be a GPE, it can be a KE, it can be a elastic potential energy, it can be work done, it can be thermal energy, it can be electrical energy, it can be magnetic energy, any form of energy, as long as that energy is being used for a certain period of time. Okay, energy can also be defined as the rate of work done, because work done is also a form of energy where an object is being pushed for a certain distance by a unit force. So therefore, power is also equals to work done over time. So this work done can be work done in many forms. It can also be similar to the forms of energy that we have earlier. Okay, let's see some example. A boy of mass 40 kilograms takes 15 seconds to run up a flight of stairs of height 10 meters. Right? What is the average power of the boy? So here, if you notice, the boy runs up the stairs. So running up a certain height, he will gain the gravitational potential energy of the boy. So according to our formula, power is equal to work done over time. So here the work is being done to run up the stairs by 10 meters. So the boy gain GPE. So he will become gain in GPE divided by time. And then by substituting the formula and the values, we will get our value as 267 watt. That means that the boy uses 267 watt of power to run up the stairs at the height of 10 meters. Okay, let's see our next example. A 15 kilowatt of pump, okay, to pump water up to a building of 100 meter in height. So what is the maximum mass of the water that can be pumped? So here the question is asking about the mass, but still they are giving you hints of power and height. So again, when the water is pumped up a building, it gains in gravitational potential energy. So according to our formula for power is gain in gravitational potential energy divided by time. All right, substituting into the formula the values that you have, right? Rearranging the formula, we rearrange to mass per unit time because the question is asking what is the maximum mass of the water to be pumped each second. So mass each second. That means that mass per time. Mass per time, make it into your subject of your equation. So rearranging and you will get the answer as 15 kilogram per second. That means every second there is a 15 kilogram of water being pumped up to 100 meters height. Let's go into efficiency now. So efficiency basically how effective if your system is, right? So it depends on if you are giving it some sort of an amount of energy to it, right? How much is actually being used? Is all of the energy that is being supplied being used or only a part of it being used? If only a part of it being used, that means it is not 100% efficient. It is only efficient at the amount that it is being used for, right? A system that is 100% efficient, the ratio should be 1. So basically, efficiency is just the ratio of the useful energy over the over the input energy, right? times 100%. Usually efficiency is measured in percentage. How many percent you are useful to compare to the input of your system. Okay, but we can also relate it to the power, where it will be efficiency equals to the rate of the ratio of useful power over the input power. So usually efficiency is replaced or denoted or represented by a Sankey diagram. Okay, the Sankey diagram is a simple diagram of arrows where there will be an input, the whole thickness of the arrow. The whole thickness of the arrow will represent the thickness of the arrow on the left hand side here will represent the input energy. All right, then the input energy will be going out to the output part of it on the right hand side, where the output part will be the portion of the thickness. Okay, the portion of the thickness of the input energy. All right. So one output will be into the useful energy and the other output will be into the energy lost. Okay, so according to the Sankey diagram, right, there is 100 joule of energy that is being input into the system. All right, but the system is only using 42 joule of energy. All right, and the remaining 58 joule of energy is being lost in other forms of non-usable energy. Right, so according to this system, the efficiency of the system will be useful energy divided by input energy times 100%. So this system is only 42% efficient, right? So if you notice that the energy loss is the type of energy that is not contributing to the main use of the system. It means that if you have, let's say you are using a light bulb, right? A light bulb, you use the light to light up the space. But the problem is, together with lighting up the space, there is also heat being produced. So the heat is not contributing to the light. It is actually reducing the light. So therefore, heat is considered as an energy lost. Whereas in a car, if you pour petrol, you hope that the petrol is 100% being used to move your car as fast as possible. But that is not possible, because as your engine starts to move, the mechanical parts in the engine start to move, it will produce heat. So heat is basically reducing the efficiency of your car. It's not producing or contributing to more higher speed. It is basically contributing to lesser speed. So it is assumed as energy lost, but lost as other forms of energy. Let's see this example. All right, a coal-fired power station generate electricity at night. Okay, it's a coal-fired power station. All right, some energy is stored by pumping water up a mountain lake. So that means there will be some water which will be pumped up to a mountain. Right, where there is a high demand electricity, the water will be allowed to flow back down. So when it is, again, the keyword here is up a mountain. All right, the keyword up. That means there must be some gain in gravitational potential energy here. So after that, during the high demand electricity, water is allowed to flow back. So that means here must be some kind of kinetic energy will be converted. All right, and then the whole energy is then converted to turn the turbines. The turbines turns means kinetic energy, and then it generates electrical energy. Okay, so that will be the main idea that we can get from this question. So on one occasion, there is a 2.05 times 10 to the power of 8 kilogram of water pumped through the vertical height. So again, here it is talking about the height 500. All right, so again, gain in gravitational potential energy or loss in gravitational potential energy. Okay, we go with the question. Question says, calculate the weight of the water. So according to our understanding, weight is given by mg, mass times gravity. So this will be a simple calculation. So 2.05 times 10 to the power of 9 Newton of water weight that is being transferred, that is being pumped. Okay, calculate the gravitational potential energy gain. So remember, as earlier in the question, we have already been getting the idea of gravitational potential energy gain. So gravitational potential energy is equal to mgh. Okay, substituting the values, h will be equal to 500 meters high the mountain. So you get a 1.025 So the answer can be rounded off to 3 significant figures or 2 significant figures to 1.0 times 10 to the power of 12 joule. All right. The next question, electrical energy used to pump the water up the mountain lake is 1.2 and only 6.2 10 power of 11 joule of energy is generated when the water is released. That means only this amount of energy, is generated, whereas this is the amount of energy that is being supplied, right? Right. So basically, after you have pumped up the water with this amount of energy, the water is allowed to flow back down, but only 6.2 times 10 power of 11 of energy, electrical energy is generated by turning the turbine. So that means there must be some energy that is already lost, probably in the turning the turbine, friction of the turbine, sound of the turbine. So that is the energy lost. So the efficiency of the system can then be calculated, right? Energy generated or energy input, right? So energy generated is only this amount 6.2, and energy input is 1.2 times 10 to the power of 12. So we get our efficiency of the system to be only 51.6%, which then can be rounded off to 52%. Okay, so in this diagram, we have learned about the whole chapter. We have learned about energy such as GPE, KE, strain, electrical, thermal. Okay, so we also know that work done is also energy. Remember that. Okay, kinetic energy is the energy of a moving object. GPE is the energy gained or lost when an object changes position in height, basically. Okay, power is the rate of energy being used or work done per unit time or energy per unit time, and efficiency is the measure of or the ratio of the input and the useful energy over the input energy. Thank you. I hope this lesson has helped you. Hope to see you. I will see you again in my next lesson. Thank you very much.